When we were talking about the induction machine back in video 15, we emphasized that there is no direct electronic connection between the stator and the rotor. The current inside the rotor is purely induced by the magnetic field created inside the stator based on the Faraday's law. If the rotor of the induction machine is not rotating, either because the end rings are open so there's no current flowing inside of it, or because we are holding it stationary, under those kind of situations, the induction machine is actually almost identical to another type of electrical machine known as the transformer. The transformer is an electrical machine that transfers electrical energy between the primary side circuit and the secondary side circuit through electromagnetic induction. So inside of the transformer, there's no direct electric connection between the primary side and the secondary side. The link is provided purely by magnetic fluxes that's induced on the primary side. So a varying current in the primary coil of the transformer is going to produce a time-varying magnetic flux because of the Ampere's law. This varying magnetic flux, it's not sort of confined on the primary side. It actually goes through the transformer core. So it actually goes through the coils on the secondary side, right? And this varying magnetic flux is going to induce a voltage in the secondary coil just through this transformer core because of the Faraday's law, right? So the relation between the primary side circuit and the secondary side circuit in a transformer is actually identical to the relation between the stator and the rotor in an induction machine. So a common approach of studying the equivalent circuit of the induction machine is to start from the equivalent circuit of the transformer. If there are any differences between the induction machine and the transformer, we then modify the equivalent circuit of the transformer and incorporate those differences gradually. And that's the approach that we're going to take in the following videos. So there are three fundamental relations for the ideal transformer. The meaning of the word ideal will become clear when we try to incorporate those non-ideal losses into the equivalent circuit. But for now, let's just consider the so-called ideal transformer. The first relation is between the voltages on the primary side and the voltage on the secondary side. So it is important to realize that it is the same magnetic flux inside the transformer core that links the primary side coil and the secondary side coil. So the Faraday's law tells us that the primary side voltage, EP, I replaced the VP to EP here. The reason is because E, those small case letters are usually used for indicating instantaneous values, right? So the voltage on the primary side, EP, right, is equal to the primary side number of turns in the coil, MP, times the temporal rate of change of the magnetic flux, phi, right? And then on the secondary side voltage, ES, equals to the secondary side number of turns in the coil, NS, times the temporal rate of change of the same magnetic flux phi. Right? It's the same magnetic flux that's linking both the primary and the secondary side. Right? So it's the same phi. This phi and this phi is exactly the same. Right? So if we divide these two equations, the left-hand side is the voltage ratio between the primary side and the secondary side. And then the right-hand side, d phi over dt cancels out if we divide them, right? and then the right-hand side becomes MP over NS. That's sort of the ratio of the number of turns on the primary side of the coil and the number of turns on the secondary side of the coil, secondary side of the coil, right? So it's a ratio of the number of turns between the primary coil and the secondary coil. The right-hand side is also known as the turns ratio, and is often represented using symbol A. In the literature, sometimes it's used, the inverse of A is represented using N, right? Using the letter N. But here we'll just use A. A is the ratio between the turns ratio at the A is the turns ratio between the primary side and the secondary side, right? So when A is less than 1, which means the primary side voltage is less than the secondary side voltage. In this kind of a scenario, the transformer is called a step-up transformer. So the voltage on the primary side is going to be increased to a larger value on the secondary side. Right? That's called a step-up transformer. Step-up transformer. Right? So when A is less than 1, so which means MP is less than NS, there are fewer number of coils, fewer number of turns on the primary side than on the secondary side. So it's just the opposite of the picture that's drawn here, right? The diagram that's drawn here, right? If A is larger than unity, then the primary side voltage is larger than the secondary side voltage, and the transformer is called a step-down transformer. And when A is exactly equal to 1, then the voltage on both sides are equal, and the transformer is called an isolation transformer. So that's sort of the first relation, right? So the voltage ratio equals to the turns ratio, right? That's the first relation that we're going to sort of have to use for an ideal transformer. And the second relation is between the current on the primary and the secondary sides. So for an ideal transformer, there are no energy losses between the primary side and the secondary side. So the power on the primary side should equal to the power on the secondary side. And power equals to voltage times current. Right? So EP times IP, the current on the primary side, must equal to ES times IS, right? Because energy must be conserved for an ideal transformer. There's no losses. Right? The secondary side voltage, ES, equals to what? Equals to, so if you look at the first relation that we have just sort of derived, so ES equals to what? ES actually equals to EP divided by A, the turns ratio, right? So we can replace ES with EP divided by A. So EP times IP equals to EP divided by A times IS. Right? And EP cancels out on both sides, right? So EP appears on both sides, so they cancel out. So now IP actually equals to IS divided by the turns ratio. Right? If we rearrange the terms, then we can get IP divided by IS equals to 1 over A. Right? So the ratio between the primary side and the secondary side current equals to the inverse of the turns ratio that we have defined here. Right? So if you try to write out the turns ratio as the ratio of the number of turns on the primary side and the secondary side, then IP over IS equals to NS over MP. Here EP over ES equals to MP over NS, right? But here IP over IS equals to NS over MP. It's just the opposite. Right. So if it is a step-up transformer, the secondary current is less than the primary current, right? And if it is a step-down transformer, the secondary current is larger than the primary current, right? So it all depends upon the value of A, basically. So if it's a step-up transformer, A is smaller than 1. So 1 over A is larger than 1, right? So that means IP is larger than IS. And if it's a step down transformer, A is larger than 1. So 1 over A is smaller than 1, which means IP is smaller than IS. Right? So that's the second relation. Right? The second relation that we have to sort of use later on. And then there is a third relation. The third relation is about impedance. Suppose there is a load. There is a load on the secondary side with the impedance ZL, right, which equals to the secondary voltage divided by the secondary current. Right, that's the load. That's the impedance of the load on the secondary side. Right. Then on the primary side, this load on the secondary side is going to appear to have a different impedance. And this apparent impedance, called ZL prime, is going to equal to what? Is going to equal to the primary voltage divided by the primary current. Right? And don't forget, the primary voltage equals to what? The primary voltage equals to turns ratio times the secondary voltage, yes. So EP equals to A times ES, right? Then what's the primary current? Right? The primary current equals to what? Equals to 1 over A times IS. So it's IS divided by turns ratio A. And then you can just rearrange the terms. So what you're going to get is A squared times ES over IS. That's the secondary voltage over the secondary current. Secondary voltage over secondary current equals to the load on the secondary side, ZL, right? The impedance on the secondary side. The impedance of the... So on the primary side, this load on the secondary side is going to appear to have A squared times ZL impedance. And A squared is the square of the turns ratio. Right? So the third relation is going to be this expression for the apparent load on the primary side, right? So the apparent load on the primary side for a impedance on the secondary side is going to equal to A squared times the impedance on the secondary side, the actual impedance, right? The actual impedance. So for a step-up transformer, this apparent impedance is going to be smaller than the actual impedance, right? Because A is smaller than 1, so A squared is still smaller than 1. Right? But for a step-down transformer, the apparent impedance is going to be larger than the actual impedance. So the equivalent circuit of an ideal transformer looks like this kind of thing. We've got like two inductors symbols, right? We have like two inductor symbols. So this part is the primary circuit, and this part is the secondary circuit, right? And then we have two vertical bars between these two inductor symbols. These two vertical bars actually represent the transformer core, and these two inductor symbols actually represent the coils on the primary side and the secondary side, right? And then the turns ratio is A to 1, right? And sometimes people use 1 to n, right? 1 to n instead of A to 1. 1 to n. N is sort of another sort of representation of the turns ratio. Right? So in this case, we are attaching a certain load with the impedance of ZL to the secondary side, right? We don't have a load on the primary side, right? But from the primary side, if I have no knowledge about the existence of the transformer and the load on the secondary side, right? I only know the EP and IP on the primary side, right? What's going to be the equivalent load on the primary side, right? So in that case, we would like to actually move the secondary side load to the primary side and then get rid of the transformer, right? How do we actually do that, right? How do we actually do that? So if we would like to map the secondary side load, ZL, to the primary side, and then we can we can use the apparent impedance expression we just obtained, right? So how do we actually simplify this circuit, right? We can replace the transformer and the secondary side load with the apparent load ZL prime, which equals to the actual load, the actual impedance ZL times the turns ratio. Right? So this entire circuit is actually equivalent to this much simpler circuit. Right? And EP and IP are going to be identical to EP IP here. Right? So all we have to do is to actually replace the transformer and the secondary load with this apparent load with the impedance ZL prime. Right? And we can also go the other way around. If there's a load on the if there is a load with actual impedance ZL on the primary side, and we would like to move that load to the secondary side, what's the apparent or equivalent load on the secondary side, right? And we can use again we can use the previous expression for the apparent impedance, but in the opposite way, right? So the apparent impedance for the secondary side load should be the actual impedance ZL divided by the turns ratio squared, right? So ZL prime equals to ZL divided by A squared, right? And if we would like to actually get rid of the transformer altogether and also the primary side circuits altogether, so all we need to do is to actually replace the secondary voltage ES with EP divided by A, right? That's the first relation that we have obtained, right? So EP over ES must equal to A, right? So ES must be equal to EP divided by A. And then the current, the secondary current IS must be replaced with A times IP, right? So if we actually do these kind of replacements for the voltage, current, and also the load, the impedance, then we can actually remove all the primary side circuits. So all these relations are for just the ideal transformer. For practical transformers, we need to account for several types of non-idealities. Right. So when we were deriving the voltage relation using the Faraday's law, when we were doing this kind of thing, right, using the Faraday's law, what we neglected was the fact that the magnetic flux inside the transformer coil is set up by passing a time-varying current through the primary side coil. And so the magnetic flux is actually induced based on the Ampere's law. The Ampere's law was discussed in video 14, right? And it tells us that the magnetic intensity H, here, is proportional to the current times the number of coils and the number of turns in the coil. And in video 14, we were sort of looking at an example of a solenoid, right? So Ampere's law tells us that capital H, the magnetic intensity, is proportional to the current multiplying the number of turns in the coil. Right? But that only tells us the magnetic intensity and the relation between magnetic intensity and the current, right? What we're actually using for inducing voltages on the secondary side is actually the magnetic flux. So to go from the magnetic intensity H to flux, we have to go through this quantity called flux density, that's B. Right? So to go from the magnetic intensity H to the magnetic flux density B, this relation is nonlinear and depends upon the magnetic material. So for alternating current used sort of in transformers and also in induction machines, so the induced H, because the current is actually goes back and forth in opposite directions, So H is going to go back and forth along this horizontal axis. It's going to sort of oscillate between positive and negative values, right? So H is going to go back and forth along the horizontal axis, right? And then as H varies, the flux density B is going to go around this so-called hysteresis loop. So the magnetic material actually absorbs energy during each cycle, and this energy is dissipated as heat. The amount of heat per cycle is actually equal to the area enclosed by the hysteresis loop. And that's called hysteresis loss. And this happens inside of the transformer core. Right? The transformer core is the magnetic material, and it also has its own hysteresis loop, right? And so it's going to have its own hysteresis losses, right? That's one kind of loss that we have to account for. And there is another type of energy loss inside the transformer core, and it is known as the eddy current loss. It's called eddy current loss. So the time-varying magnetic flux set up inside the transformer core is going to induce voltages not only on the primary and secondary side coils, but also inside of the transformer core. The transformer core has a finite resistance, right? Usually it's made up of iron or some other kind of a conductive material, actually. So once you induce a voltage on the transformer core, and because the resistance is finite, this induced voltage is going to generate a current inside the transformer core. And then if we sort of take a look at this vertical cross-section, if we take a look at this vertical cross-section here, if we take a cutout of view about the vertical cross-section, right? Suppose the magnetic flux goes along this green arrow, that's B, right? That's the flux density, right? Then the eddy current is going to go around these green circles, those red circles, these red circles. That's the induced eddy current inside of the transformer core, right? That's what the eddy current is going to look like. And this eddy current is going to dissipate power, right? And the amount of power that's going to be dissipated by this kind of eddy current equals to the square of the eddy current strength multiplying the resistance of the transformer core, right? Which is actually a result of the Ohm's law, right? The power equals to what? The power equals to voltage times current, right? And then the voltage equals to what? The voltage equals to current times the resistance, right? So voltage times current, the power equals to what? The power equals to current squared times the resistance, right? And now because you have eddy current, and then because you have resistance inside the transistor core, transformer core, then you're gonna dissipate power. You're gonna dissipate power, and that power equals to the strength of the eddy current squared times the resistance of the transformer core, right? Which can be actually quite significant if you don't do something. So the strength of the induced eddy current is actually proportional to the magnetic flux enclosed inside of the eddy current circles, right? So if you have less amount of fluxes that goes through those kind of red circles, then the strength of the eddy current is going to be reduced, right? So how do you actually reduce the eddy current losses, right? So in practice, what people do is that they don't use they are not using a iron core, right? They're actually using the transformer core is usually built up of lots of very thin insulated laminations of those magnetic materials. right? Because the eddy current cannot flow across the laminations, so the size of each of the circle is kind of limited, right? It cannot actually go around the entire thing because it's insulated across those different laminations. So the current cannot actually go across those different laminations. If you make those laminations really thin, then those eddy current, the size or the area that's going to be enclosed by those eddy currents is going to be really small. If the area is small, then the amount of magnetic flux that goes through each of the circle is going to be very, very small, right? What I was just saying is that the strength of the current, eddy current, actually is proportional to the amount of magnetic flux that goes through it, right? So if you make the cross-sectional area, the area enclosed by the circle very, very small, then the amount of flux goes through it is very, very small, right? So the induced eddy current strength is going to be very small. So that's what people actually do to actually reduce eddy current losses. They stack the transformer core by using lots of very thin insulated laminations. And this is another kind of loss inside of the transformer core, right? So to account for both types of losses inside the transformer core, we add a resistor with the resistance R0 to the primary side of the circuit. So the energy dissipated by R0 should be equal to the hysteresis loss, right, plus the eddy current loss. So the circuit to the right side of this resistor R0 is still an ideal transformer, right? But there's a current junction on the primary side now, right? That's the current junction. That's a node, and at this junction, the current IP flows to the ideal transformer, and a small current I0 is going to flow to furnish the core losses. Right, it's going to go through the R0 to furnish the core losses. Back in video 14, when we were discussing the Ampere's law, we introduced the concept of magnetic permeability, which is basically the slope of the BH curve. If the permeability is infinite, which means that the BH curve is vertical, then it takes zero current to set up the magnetic flux, right? Because the horizontal axis is h, right? H is proportional to the current. If the BH curve is vertical, then it takes zero current to actually reach the BS, the saturation magnetic flux density, right? But the magnetic material making up the transformer core has finite permeability. It's not infinite permeability. It's a finite permeability, which means that the BH curve is going to have a finite slope. It's not going to be vertical. It's going to have a finite slope. So if it has a finite slope, then it's going to take a finite amount of h to reach BS, right? A finite h means finite current I, right? Because h proportional to current I, right? So it takes a finite amount of current in order to actually set up the flux inside the transformer core. So to account for this finite permeability of the core material, we add an inductor with the reactance X0 parallel to the resistor R0. So the current I0 now flows into two branches. A portion of it is used to set up the magnetic flux inside of the magnetic material with the finite permeability. And then the remaining part is going to be used to furnish the core losses. And X0 is called magnetizing reactance of the primary winding. So that's for finite permeability of the core material, right? And then the magnetic flux set up by the primary side of circuit, is not all confined into the transformer core. And some of the fluxes are going to be leaked outside of the core. Right? So you can sort of see those flux lines. Some of them are going to go outside of the core. It's not all confined into the core. Right? And those leaked fluxes, because they are not inside the core, so they do not contribute to the electromagnetic induction processes inside the core. So they are not exactly contributing to the transformation process, right? That's kind of a result of the electromagnetic induction process inside the core, right? But because there are still sort of induced voltages, there are still induced fluxes, so they are still going to induce voltages. But it's a small amount of voltage. It's a small amount of voltage because the amount of fluxes leaked outside of the core is kind of small for realistic applications. But you still have some amount that's leaked outside, right? And this kind of leaked voltage is going to induce a small amount of voltage, right? And on the secondary side, if the secondary side is kind of connected to a load or something, and then it's going to have current flows in the secondary side of the coil, and those induced current is going to produce its own, it's going to create its own magnetic field, right? And that magnetic flux is also going to have a leakage, right? It's not all confined into the core either, so it's also going to have leakages, right? So to account for those leaked fluxes that do not contribute to the electromagnetic induction processes in the core, but still contribute to the induced voltages on both sides, we add an inductor. We add an inductor with inductance X1 to the primary side, and then an inductor with reactance X2 to the secondary side. Right. So these two inductors accounts for the leakages, the flux, the leakage fluxes. Right. And finally, we have resistances inside the primary and secondary windings. We add the resistor with the resistance R1 to the primary side, and then the resistance with the resistor with the resistance R2 to the secondary side. So these two resistors account for the copper losses, the resistances in the windings, in the wires, in the coils, on the primary and secondary side. Right. And then the circuit inside of this blue box is an ideal transformer, and all the non-idealities of the practical transformer have been accounted for by the circuits outside of the blue box. So by now we have obtained the equivalent circuit of a practical transformer. It will be the starting point for us to study the equivalent circuit of the induction machine in the following videos.